Okay, can you see my screen?
Yep.
Okay, so or I'm going to start with the Euclidean algorithm. Okay, so this one was fairly simple for me to implement. So I'll just take you through it. So our function is supposed to take in two numbers, A and B, the one that we're referring to as A and B, and it's returning the GCD of the two numbers. So the first part, the first two if statements, cater for when one of the numbers is 0, so it returns the other number, the second number. So now from the third if statement is when the two numbers are not equal to 0. So first of all, I check for the one that's greater, because we want the number that's greater to be, because we usually write it as A is equals to B times X plus the remainder. So I want the greater number to be A and the smaller number to be B. So I first of all check for that. And then while our remainder is not 0, because we said that the GCD is supposed to be the less than 0 remainder, we will perform this loop. So first of all, we'll store our first number in a temporary variable, and then we'll store a second number in A, and then B will hold the remainder of A and B, the two numbers that we gave at first. So B is and then it will loop until our B is 0. So right before our B is 0, it's supposed to return that remainder, which is now our GCD. Yeah. So I tested this function with a few of the examples that we used in class, and it was giving the right answer. So like for 816 and 44115. So yeah, it's 1. Okay, wait, let me use another example. For example, this one here, 60 and 33, the GCD is 3. So let's start. Yeah, it's giving us 33. So that's how I implemented the Euclidean algorithm. Is there any question? Okay, so if there's no question, I'll move to the extended Euclidean algorithm. So this one was a bit more difficult to implement, because we also had to, especially for the parts where we were rewriting the GCD using the two numbers. So, but first what I did is I created variables for the quotient and the remainder. So our function is taking in two numbers, the number that we're trying to find the GCD for, and then it's going to return the GCD and X and Y. And we're going to use signed integers because sometimes the answer is usually negative. Okay, so first of all, Q and R. Q is a quotient. It will track our quotient. Like we said before, it's written as A so our X, or let me just write Q. This is our Q and our R is the remainder. And then the X1, X2, X3, and Y1, Y2, Y3 is what we're going to use to track our X and Y values and updating them as we loop through the while. So first of all, like in the first question I did first, while our remainder is not equal to 0, we're going to store the A divided by B in Q and the remainder in R. And then X3 is going to, at first, X is going to be, X3 is equals to 1 minus our quotient, which is going to be A divided by B. And then we multiply it by 2. So at first we're using 1 and 0 so that our values, like, so that, okay, we're initializing X1 and X2 with 1 and 0. And then, okay, our X3 will not be read at first. And then we're also going to add the condition for where B is greater than 0, because if our second number is 0, we're going to get an error, this error here. And then after we update our quotient and R, X3 and Y3, we're going to again update A, B, and the other X's so that we can repeat the process until we get to the less than 0 remainder. Yeah. So here I also tested with 60 and 33. Yeah. In the question, like in our notes, our X is 5 and our Y is -9. So if we try and run our program here, yeah, it's giving us 3, 5, and -9. So in the first question, I had not considered when the situation when B is equals to 0, but we were to update it because when B is equals to 0, when the second number is 0, we're going to get an error. Okay, and then is there any question? Okay, so I think I'll finish with the code for congruence. So for congruence, we're supposed to first of all find if we have our two numbers. So if we have A, C, and M, we're supposed to find M is the mod, right? So A is equals to C mod M. So we're first of all supposed to find GCD of A and M, and then check if it can divide C. And if it can divide C, then that means that we can find solutions. And if the GCD is 1, then that means it has one solution, and so on. So I used my same code for the extended Euclidean algorithm so that we can find the GCD and X and Y. And then now in congruence, when we have our two numbers, our three numbers actually, we're supposed to, first of all, find our GCD, which is going to be D here. And then we check if D divides C. So if it is equals to 0, then that means they can divide. And we continue with the process. Otherwise, we're supposed to return, okay, here I'm supposed to update it to return an error. Otherwise, okay, our first value is supposed to be our X. So from the extended Euclidean algorithm, we know X is so X is multiplied by our first number, and then Y is multiplied by the second to give us our GCD. So it's supposed to be to find the first value, the first solution for our congruence. It's the X times the quotient of our second number divided by the GCD of A and M, and then we find the modulus of all of that, and that will be our X0. But my code is currently incomplete, actually, I've realized, because it can't find other solutions. Yeah, if there are 2 or 3 solutions, we can only find one. So I need to check on that. Okay. Yeah, so I tested it with can't find. Let me just use 59 and 57. I believe this one had 3 solutions, but we can only find one for now. Yeah, 12. Let me check the notes. Okay, I can't remember which lecture it's in. Yeah, but it has 3 solutions, and I've not implemented the part to find the rest. Okay, yeah. That's how I did the 3.
Awesome. And maybe you can get a comment from Walimu, and then if anyone is good to test their squid up, just type in the chat, and then we'll do that after Walimu. Yeah, just give us some feedback.
Thank you. I'm very happy with the work I'm seeing, because that is the aim of what we are doing, so that you are able to implement it in codes. I'm very happy. I think that is how we're supposed to progress. A lot of exercise so that we can implement this in programs. Now, there's just that one point she has talked about.
Amalimo, I think you have a connectivity issue. You're breaking up.
The issue of getting the three solutions, maybe I just want
Malimo, I think we're struggling to hear you.
to repeat how
I
we
think
were
you have
getting the three solutions, and I don't know how she'll do it so that she implements. Once you have that last equation has given you the first solution, let me call the first solution 10. Now to get the other two solutions, you taking the m, that is the mod of that last equation. Can you hear me now? Ocheng, can you hear me?
Yes, we
Anybody who
can hear you.
me?
Although I think there's a lag. I think you have a lag. But just continue.
So I don't know. Is it an issue of network?
I think you're good now. I just continue. Let's see how it goes.
Okay. So I was explaining what Lynette talked about, and she was not able to get the three solutions. I was just trying to make it clear so that she goes and tries again, see if she can get the three solutions. So I said once you get the first solution, which we call x1, you have that last equation. That last equation that has, after dividing by the GCD, you see, after you find the GCD is 3, you divide through by the GCD. So the equation that you get has a mod m. So that mod m, we add to this x1, gives you the second equation. Now that second equation, add again m, that mod, that gives you the third equation. Alternatively, the other way you can say is that take that x1, that first equation, then plus mi, where I is 0, 1, 2. 0, 1, 2. So that when I is 0, it gives you the first equation that we got. When I is 1, you get the second solution. And when I is 2, you get the third equation, the third solution. And I think that is the only thing I wanted to repeat, so that if it was not very clear, then she can now go and try. But thank you, Lynette, for the good work.
Okay, thank you for that. I will implement that. Thank you.
Yeah, thank you so much, Lynette. I don't know, does anyone have any questions for Lynette? All right. 1 second. Seeing some questions. All right. Has anyone managed to set up Squid app on the Android phone. You can provide the link. All right, so I think we'll just continue with classes. There's no one yet. We can, if someone manages to do so during the course of the class, you can feel free to demonstrate or do an exercise. I will also give it another go tomorrow because the communication came out a bit late. So yes, Mwalimu, yeah, kindly proceed.
Okay, I wanted to ask whether you are seeing my screen. Just a minute, let me again share. Can you see my screen?
Yes.
Yes, yes.
Okay. And so I want to see whether you can also see when I write. Can you see when I write?
Yep.
It's okay. So today I want us to look at how to keep our communications secure, and not only communications, but even human activities like finance and voting through encryption. So I'll be looking at RSA so that you can also try and implement that. Now, last Thursday, we looked at primitive roots, but the quorum was not okay. So I think I'll repeat the same next time. But today, let's look at RSA. I would have begun with the ciphers and so on, but I thought that since you had discussed RSAs sometimes back in your classes, we just finish with it, and then I'll come back to ciphers later. No, so as I had already said, this is just a way of trying to ensure that our communication and other human activities like finance and voting are secure. And it's not like in the past where one would communicate, two people but is hearing their conversation. But today, because of the RSA and the ciphers, you can communicate knowing that you have people who will try to get to know what you are communicating. But because of the security that you put on your communication, they cannot be able to know what you are communicating. So I just began by definition of some terminologies. I'm sure you are aware of, you already know these definitions, but just for the sake of having the whole content covered in the same, I decided to try and define what a plain text is. And this is just the original text that you have, and you want to send it to your colleague or your friend. So we shall call it plain text. But you don't send the plain text. This is what you have. So what you do, you try and encrypt it, so that if the enemy was able to meet your communication, will not be able to know what is inside. For instance, I want to send you some message like like come, we meet at the office. But what I do then, I encrypt so that I just send you digits. I send you digits. So it's only you who can know what those digits mean. But any person wanting to know what we communicated may not be able to find out what we communicate. So that is what you send to your colleague is what we then call a ciphertext or an encryption. And when your colleague then receives that, he performs what we call decrypting. So it decrypts your ciphertext to get back the plain text that you had intended him to or her to read. So those are the terminologies that we'll be using. So suppose I want to send you a plain text. I had already said that I'll then encrypt this, and so I'll be using some keys. The keys I'll be using, it's you who gives those keys to me. They're not mine. So it's you that, because we are using the RSA, the person that is receiving the communication is the one that comes up with the keys, and we call those ones the public keys, them private keys. So what is important in this lesson is how do we come up with the private keys and how do we come up with the private keys. So the public keys, the person whom I'm supposed to send in communication to comes up with those public keys and gives them to me. Not only me, because of this RSA, if let me say it's Ocheng that once comes up with the public keys. So these public keys, Ocheng will announce them to anybody, any other person. And another person that wants to communicate to Ocheng will then be using those public keys to encrypt the message he wants to send to Ocheng. So Ocheng has those two. There are just two public keys. And then he publicizes it. Those keys, he sends them, could be over internet or even magazines and so on. And then if I'm somewhere in Kisumu and I want to communicate to Ocheng and I have those public keys, then I'll use them to encrypt my message. Once I encrypted my message, Ocheng has other keys, which we call secret keys, that he'll use to decrypt whatever I send to him so that he can be able to read my initial message. Now, so I just want to take you through the steps, how it works. And that's what I've just said. So suppose I want to send you a message. Suppose I want to send you. So if I'm to send you a message, then it's you to come up with the public keys. So to do this, you, the one whom I want to send a message, would come up with the public keys. That normally two. They comprise of two. There are two public keys. Now, before you come up with those two public keys, you pick two prime numbers. You pick two prime numbers. Let me say you pick 11 and 17. And those two prime numbers should not be equal. Now, for purposes of this class, I'll use smaller prime numbers so that we can do our calculations the same way we've been doing. But for purposes of securing your message and securing things that you love, like finance and voting and so on, you are supposed to choose very large prime numbers. And this is what somebody had asked earlier, the importance of prime numbers. And we are saying that if we choose two big prime numbers, and later those prime numbers, for instance, 3, if I were to multiply these two prime numbers, the result is 21. To factor this number is not easy. If it was a big number, it's not easy because the only numbers that will factor them are these two. It's unlike 12. If I had a 12, I know 2 can divide this. So factoring this becomes very easy. I know at this point 2 again, but supposing I have 21, 17 and 11, and I multiply and I get a number like, let me say 187. It's not easy to know which numbers can be factored out of this. So that is why we say prime, it's easier to tell what was used. We're using bigger prime numbers to secure our message. I've said I want to send a message to you, and since it's you that will be receiving this message, what you then do, you pick 2 prime numbers. And let me say, I've said, let's suppose you picked 11 and 17. The second thing you do, it's you that I want to send message to, you would calculate the product of those 2 numbers. Calculate the product of those 2 numbers. So you chose 11 and 17. Get the product. This 11 and 17, you don't tell anybody. Once you choose them, those 2 prime numbers, you make them a secret. You make them a secret. They're yours. Nobody should get to know what they are. Because if somebody gets to know what they are, whatever message you'll be receiving, that person would be reading that message before it reaches you. So you keep them a secret. Then get their product. After getting their product, the other thing you do, you get, so let me say the product is this 117 and I want to call it M. Get the phi of M. We talked of phi of M. The number of elements or numbers smaller than M and relatively prime to M. Find how many they are. And if we are talking of only 2 prime numbers, and then those phi of M is easily given by that. P minus 1 multiplied by Q minus 1. So in our case, P minus 1 will be 10 and Q minus 1 will be 16. So when you multiply, our phi of M will be 160. Now, who is doing this work? The person who will be receiving message, the one I want to send in my message to, is the one who does this. There must be bigger prime numbers, gets the product of the product. 5 follows is that this prime to this, a number that is relatively prime to phi of M. And that number, I want to call it E. So that is my next step. That number, so you choose, this number is, I've called it E, but what is it? It's a number which is relatively prime to phi of M. That is why you are calculating phi of M. You must know what phi of M is, and then find E. So what we are saying is the other way of writing, because you are doing a program, the other way of writing phi of M should be 1. So you choose an E such that the GCD of E and phi of M is 1. That's what we just meant, that it must be coprime or relatively prime. And another condition, that E should be smaller than phi of M. Should be smaller than phi of M, but should be larger than 1. So that one you just choose. There's no calculation there. Let me say, let's choose 7 in our example here. You had chosen 11 as a prime number. You had chosen, what was the other one? Was it 17? 17 as the other one. You found the product to be 187. You found phi of 187. 187, and you found this to be 160. Now the second task you have, before I send you my message, is pick a number that is relatively prime to phi of m, and you've chosen 7. After choosing 7, find the inverse of 7. And that's what I've written here. Find another number d. Just before you find that d, let me say that this e is a public key. You will send it to me. You will send it to me so that I send you my message. The other thing you will send to me was that 7. So you will send me 2 public keys. One is M, the other one is E. M, remember, is the product of the 2 prime numbers you picked. Now, after picking those 2 prime numbers, you found Q of phi of M, and then picked another number, which is relatively prime to this. That number, you will send it to me. It's also a public key. You will publicize it. Anybody who wants to send you a message, let him have these 2 numbers. Now, this number is important because it will help you to calculate D. D, I've said, is the inverse of E. We know how to find the inverse. Extended Euclidean algorithm, extended Euclidean algorithm. We also, in another lesson, learned how to use the Euler's theorem. Euler's theorem. So you have 2 ways of finding. You have 2 ways of finding a inverse. I know we learned about the phi, the formats, but the formats will not work here because this phi of m is not prime. Is not prime. If it were prime, then you would have used the Fermat's little theorem, but it's not prime. So you are only left with these 2 methods to use. Any of them that would be easier. But it's important that this D is a private key. You don't expose it to anybody. So what you should not expose to somebody is the P you picked, the Q you picked, and then this D you've calculated. You don't expose it. And in fact, don't expose phi of m, because anybody who discovers what phi of m is able to find the prime numbers you used. This person can work out until he finds, because we've said that phi of m is just given by p minus 1 multiplied by q minus 1. So if somebody has a hint what q of m is, this person is able to get what p is and what q is. And if this person gets to know what p and q are, then it's easy also to try and find. You see, once I have this, I can try and find which numbers are relatively prime. So I'll be using trial and error. And by that trial and error, I may be able to decrypt your message. Now, so those are I've talked about the private and the public keys. And so what follows, therefore, is just the calculations. How do you encrypt and how do you decrypt a message? How do you encrypt and how do you decrypt? Now, so that is what I want now to explain. But first, before I do that, I'll just repeat what I've said so that you get to know, you understand before we proceed. I said I want to send you a message. You pick 2 prime numbers. You pick 2 prime numbers which are not equal, and we said P or Q, P and Q. And the second thing you do, find their product. Let's call it M. And then find phi of M. And this is just given by P minus 1 multiplied by Q minus 1. This P and Q, keep them. They're a secret. Keep them a secret. This M, you will announce it as a public key. Once you have this phi of M, choose a number E, which is relatively prime to Q of M, so that the GCD is 1. Pick, that one just pick. So in our case, we had picked 7. After picking this number, together with M, announce them as your public keys. So this is the key that I use for encryption. Encryption, I'll be using this key. Now, this E, use it to find D. And you've said that D will just be the inverse. The inverse of D will be the inverse of E mod M. Not mod M, not mod phi of M. Mod phi of M. Not mod M, but mod phi of M. And I said you can use either method that we learned. Now, you made this public. I have this message I want to text. I want to encrypt it. How do I encrypt it? I just take my message and raise it to E mod M. Remember, you had also made M public. You had made M public. So I have it. So since I have it and my message is X, this is my message will be that way. That's now the encrypted message. That is the encrypted message. That's the message I sent to you. So let me say, in this case, let me say that my message was 99. And your M was 187. You sent it to me. And you had chosen E to be 7. So these two are public, are in the public domain. Everyone knows about them. And I know I have this message I want to send to you. So I'll take my 99 and raise it to 7. And then mod 187. I use the first power algorithm to find that. And then I send it to you. Now, when you get that message, you're supposed to decrypt it. How do you decrypt it? To decrypt, you take the message I sent to you. This is my message I sent to you. You take the message I sent to you, and you remained with some private key, this MD, no, the D here, and you have this M. So this is the key for decryption. Once you get my message Y, raise it to D mod M, and you have my plain text. So you can read it and see what I wanted you to know. So in terms of numbers, let us now do it in terms of numbers, because I've already shown you what to do. And of course, that is how you do the RSA to encrypt and to decrypt. And of course, to come up with the keys. And the person who is supposed to receive your message is the person who comes with the public keys and sends to you. And that person remains with a private key to decrypt your message. Any message, not only yours, but anybody else who wants to send this person a message will be using the public key to do that same public key. Now, so you had chosen 7 as your E and your M was 187. You sent those ones to me. My message was 99. So I take 99 and raise it to 7, and I do it mod 187 using the fast powering algorithm. I will do that and get 176. So you know what we normally do. Fast powering algorithm, what you normally do, you take 97, 99, raised to 1, find what it is. What about raised to 2? Find what it is. What about raised to 4? Find what it is. What about raised to? Now, when you go 8, it's beyond. So then you say 99 raised to 7 will be the same as 99 raised to 4 plus 1 plus 2 plus 1, because 4 plus 2 plus 1 is 7. So this is the same as 99 raised to 4 times 99 raised to 2 times 99 raised to 1. Now let's just see what it is. But when you use your calculator, we already did this, you'll find 176. We are doing it mod 187. We are doing it mod 187. So 99 raised to 1 will just be 99. What about 99 raised to 2? You get 9,801. Then divide by 187, our mod. It goes there 52 times. What is the remainder? The remainder is 77. We are doing it mod 187. What about 99 raised to 4? It's just the same as squaring this. When you square this, so it's 77 times 77, you get 5,929. Then divided by the mod, which is 187. 187. What's the remainder? I said 30, 31 times. Eh? How many times did it go there? Just a minute. I've forgotten the number of times it goes there. It goes there 31 times. 31 times. So the remainder is 132. Now you're here. You're here. 99 raised to 4 is 132. 99 raised to 2 is 77. And this other one is 99. We are doing it mod 150, 187. So 132 times 77 times 99, I get, is it 1 million? Then divide by 187. It goes there how many times? Let me just write. It goes there 5,380 times. So find the remainder now. 5,380 times. The remainder is 176. So this is the message I sent to you. This is my encrypted message. So when you find this message, you're supposed to use your private key to find my encrypted message, my plain text. So let me just erase this. Now you have my 176 message. 176, that is my encrypted message. When you get it, what do you do? You take 176 and raise it to your private key that we had calculated, D, the inverse. It was the inverse of 7. Just erase this. So what was the inverse of 7? The inverse of 7 we had found to be 23. We had found to be 23. So when you get my 176, raise it 23 and use the fast powering algorithm, mod 187. So that is what we did. That's what I did. And when you do that, you would get my message, which was 99. And this one, again, you're using the fast powering algorithm. That is 176 raised to 23 mod 187. So first of all, you find 176 raised to 1, 176 raised to 2, 176 raised to 4, 176 raised to 8, 170 raise it again, it will go beyond 23. So that is enough. So you find what this one is, and you are doing it mod 187, and then multiply those. Now, let me take you to another example. Now. Just before that, I want to give you a summary of that algorithm, the one I've just, without mixing it with an example. Let me give you the summary of that algorithm that I've just talked about. So this is the summary of the algorithm, and I just repeat what I've already said. That you want to send, suppose you want to send a message, and the message you want to send to your friend is X, and that is what we call the plain text. This is your plain text. That's the message you have. So you not send this message before you encrypt it. You have to encrypt it. Friend whom you want to send, first of all, product. And those two prime numbers are very huge prime numbers in the future. And that person will be using that public keys. There are only two public keys, which is just obtained by getting two prime numbers should be kept secret by your friend. So after choosing these two prime numbers, your friend is supposed to calculate Q of M, which is calculated by that. And then your friend is supposed to choose another public key, E. And we said this E is supposed to be relatively prime to phi of M. Supposed to be relatively prime to phi of M. In other words, E, the GCD of E and phi of M, this GCD should be 1. This GCD should be 1. So these two must be relatively prime. The E, just choosing. This one you're not calculating. But after choosing E, you have to calculate its inverse. And that inverse is what we call D. Calculate the inverse. That inverse is what we call D. This D is a private key. The friend remains with it. So the friend has to make public this key and this. So this is the public key. M and E. M was just obtained by multiplying the two prime numbers, and E was just chosen. For instance, if my product is 12, let me say I had this prime number and I have this other prime number. The product is 15. I have to choose a number E, which is relatively prime to 15. So you just choose any, apart from 1. You don't choose one, but numbers which are relatively prime here, to 15 could be 2, could be 4, 6 is not, 7 is relatively prime, 8 is another one, 9 is not, 10 is not, 11 is another one, 12 is not, 13 is another one, and the 14 is another one. So you just choose any. Any will be E, so long as it's bigger than 1 and is smaller than m minus 1. Is smaller than m minus 1. Just choose any. So there's no formula there. After choosing this E, you have now to get the inverse. And get the inverse, you can use either the inverse of E. You can find either using extended Euclidean algorithm, or you can use the Euler theorem, the Euler's theorem. So you can use that. So now the key, that ME will be the key for encryption. That is the key that is made public to everyone that may want to send a message to your friend. Now, but D, the friend retains the D, and so the friend will be using MD to decrypt, be using it to decrypt. So this one is a private key for decryption. Now, so your message was X. Your friend has already sent you ME, and your message is X. So you want to encrypt it. What do? We said you take X and raise it to E. Let's call it Y. That is now your encrypted message. Send it to your friend. When your friend receives this Y, your friend will raise it to D. Remember, D was his message. This one you're doing this one mod M, and your friend is also doing this mod M. When your friend does this, you will get your original message, which was X. I want to look at 2 examples. I hope the explanation for that algorithm is clear, and the good thing it's recorded so that it can be used at any given time. We look at 2 examples and they'll make this clear. So this is just explanation of how you encrypt and how you decrypt. I've already explained that. That is the explanation. Now the example is here. Suppose that Alex chooses 2 prime numbers, and Alex decides to choose 11 and 17. So Alex is the one who wants to receive messages from people. Has chosen 2 prime numbers. Has chosen 11 and 17. What Alex would do would compute their product. And their product, when you compute this, you get 187. And then Alex will choose a number that is relatively prime to phi of m. In fact, phi of m, Alex will want to compute what phi of m is. Phi of m is 10 times 16, which is 160. Because these are 2 prime numbers, so phi of m is just p minus 1 multiplied by q minus 1. So my p, the p for Alex is this 10, 11 minus 1 will be 10, and then this other one minus 1 will be 16. So Alex would have gotten 5m to be 160. Then it chooses a number 2006, no 7. Yes, chosen 7. So what are the public keys that Alex is supposed to announce? N is the product of those two. So even this one is supposed to be phi of n, not phi of m. So Alex, after finding this and choosing this, announces over media the key, the encryption key. Now, when after people receive this, they'll encrypt messages. Alex will be decrypting using D. It's supposed to be ND. So let's find D for Alex. Let's find D, what his D is. Although it's his private key, we may not know, we are not supposed to be privy of it. But since we have been told what the numbers he chose, we can calculate it. So it's supposed to be the inverse of 7 mod phi of n. So this is the same as the inverse of 7 mod phi of n. Alex calculated, and it was 160. It is here. It's 160. Now, how do we find the inverse here? We have two options. Let's pick one. I want us to pick the extended Euclidean algorithm. Let's pick that and do it. In another example, we shall use the Euler-Phi theorem. So we are using, let me just use even the Euler-Phi. The Euler-Phi, the inverse of 7, Euler-Phi says to be same as 7 raised to phi of m minus 1 mod 160. So what is phi of this number? Is supposed to be phi of 160. Let me not, yes. So where m is 60 in this case, it's supposed to be phi of 160. So what is phi of 160? Let's just see. 160, 2 goes there, 80, 2 goes there, 40, 2 goes there, 20, 2 goes there, 10, 2 goes there, 5, and 5 goes there, 1. I think I'm okay. I think that is okay. So the 60 has which prime numbers? 60 has 2 as a prime number, and it has 5 as a prime number. So that means, these are the prime numbers. That means phi of 160, therefore, is a half, and that a half is this 2. Is in fact, you know the formula. The formula is always 1 minus a half times 1 minus a fifth, and then times 160. So that's what I was writing here, because this will be 4 over 5, then times 160. So this one, is it 64? Is 64.